Today we're looking at polynomial functions. You may have noticed that we don't necessarily go in order by the sections of everything that we do, but that doesn't matter. What we need to talk about today is different degrees. Our last unit was all on quadratics. You're already familiar with constant, which is a line y equals a number, which would be a horizontal line. And then you've got your linear equations, which are simply lines. Okay. Then you've got, if it says degree, now what do I mean by degree? So we're going to talk about different things besides quadratics and lines. So we're going to need to know what the degree of the equation is. It's the highest power. Okay. So a polynomial function is a function of this form. Now all these letters, that's what looks kind of ominous to you. So let me just explain more in layman's terms what all this means. A sub n is simply the constant or coefficient, whatever the number is, in front of the highest power. That's all it is. You want to order them from highest to lowest power. That's all that is. Okay. So a and n cannot, n cannot equal 0. Okay. The exponents are all whole numbers. That's important. So they can only be 0, 1, 2, 3, 4, 5, 6, and up. Okay, they have to be, the coefficients have to be all real numbers, all right? So a sub n is the leading coefficient, and a sub 0 is the constant term, which means it's the last one in the order from highest power to lowest power. So all this is, you don't have to really memorize what this is. This is just telling you to put them in descending order, highest power to lowest. Very simple. Okay, you will need to know what they're called. A constant would be degree 0, meaning there's not even an x in the term. Okay, a linear is going to be an x to the first. We already did a whole unit on quadratics, which was x to the second was the highest power. Then you're going to have cubics, quartics, quintics, and then anything 6 or above we'll just call degree of that degree, whatever the highest power number is. So these are not polynomials. Why is this one not a polynomial? Because that would be x to the 1/2, and 1/2 is not a whole number. I had to get a red pen to write on this blue background. Okay, so it said the coefficient, the powers had to be whole numbers. So you can't have a root on a variable. No roots are polynomial functions. What's wrong with this one? Well, this would actually be x to the -2 plus x to the -1, right? And -2 and -1 are not whole numbers. All right, you can't. And so another way to say it, no variables in the denominator. Okay. And for C, this is a variable as an exponent. Can't have that. No variables as exponents. My pen just froze. No variables as exponents. Okay, but this one is. Okay, why? Because what would the coefficient of x cubed be? One half. That's the coefficient of the x cubed term, 1/2. All right, you need to know that. You could change that to 1/2 times x to the third, all right? Okay, so that one is just fine. 3 is the whole number exponent, and 1/2 would be the leading coefficient. Okay, so now we've got a table. Standard form is when you have written everything with the highest exponent first and then go in decreasing order. That's all this big chart was about right here, okay? Decreasing order. So we're going to write sure these are all in standard form, and we're going to say what the degree is, etc. This one is not in standard form, so we're going to rewrite it. F of x is equal to -3x to the 4th plus 1/2 x squared minus 7. So this is of degree 4, That's the highest power. This would be a quartic because it is a power of 4. The leading coefficient would be -3. And I'm going to tell you now that if it's going to be, this one would open, which way would it open? Okay, so based on your knowledge, previous knowledge from parabolas, you would expect this to open down. It's an even power, so it's going to be something like a parabola, and I'll give you a hint. And we're going to draw all of these and talk about them in just a few minutes, but it's something like this, possibly. Okay. The next one is already in the correct form, so standard form, just rewrite it, showing that it was already in descending power order. This would be degree 3, which is a cubic, and the leading coefficient is 2. Since it is a positive 2, it's going to do something like this. The next one, we would need to rewrite f of x equals 2x to the 5th plus 6x squared plus x. Its highest power is 5. That's its degree then, and it would be a quintic. The leading coefficient of the highest power is again 2 for this one. It is an odd power, so it's going to do something possibly like this. And I'll explain later why I have it drawn like that. And then the last one here is, it is a polynomial function. It's pi x squared minus 0.5x minus the square root of 2. This is its second degree, so it would have been a quadratic. Oops, I started. Yeah, that is a Q. Quadratic. And the leading coefficient is pi. And you guys should know what that would look like. It's a positive pi. Pi is a real number, so it would open up. Okay, does anybody still need this? I can hold off a second. Okay. One way to evaluate a polynomial function is to do direct substitution, which is basically the only thing you've ever known about. You're going to find out that there is something called synthetic substitution, which I will be teaching you in this unit. For example, f of x equals 2x to the 4th minus 8x squared plus 5x minus 7 can be evaluated at x is 3. So the notation would look like this. The f of 3 equals, and then we plug it all in. Go ahead and type away on your calculator. And I'll do it without one. Okay, I'm just kind of actually being lazy, and my computer is running very slow, so I didn't really want to open up the app of my calculator. So I'm getting 105 minus 7. It should be 98. Does everybody know how to type in the exponents? If you do not, tell me please, so I can show you. Use the arrow up key. All right. Everybody able to get 98? That's all I need to know. All right. Substituted it in. So the next, some students find it, no, we're not going to use that, so just kind of ignore that little section. I'm not doing that. I want us to evaluate this by hand, not use some store function. And that's only if you wanted to do repeated, whole bunch of values in there, so we're not even going to discuss it. 3 times the absolute value of 1 minus 2. Remember to do what's inside the absolute value bars first, which would be -1. Then you should know the absolute value of -1 is 1. And that's 3 times 1, which is 3. Careful when you substitute in -2 for number 7. Excuse me, I really guess I could have put in the proper notation here. I was putting in 1. So it would be the f of 1. So this one is going to be the g of -2. 4 times negative 2 quantity squared plus 2 times negative 2 minus 1. I often think we're better off just doing it without a calculator than we are with one, simply because you guys probably know that negative 2 squared would be positive, I hope. Negative 2 times negative 2 would be 4. Then we'd have plus negative 4 minus 1, so this would be 16 plus negative 4 minus 1. And 12 minus 1, we should get 11. Okay, I want to get to something new, which is on the next page. This isn't actually very new at all to plug in this stuff. Okay, now we're just getting used to this function notation. We're on the back of 1B now. You have to pay attention. This says do the C of negative 2, so you go find which function, because we've got 2 of them here. This is the C function and the D function. The C function squares its input, so it's going to be the C of negative 2 will be negative 2 quantity squared minus 2 times negative 2 plus 1. That's going to give us positive 4 plus 1. Okay, because when you square negative 2, you get positive 4, and negative 2 times negative 2 is 4, etc. So we've got 9. Now let's get to something more interesting, where we're plugging in 3a. So what does it say to do? Well, we're putting 3a into the D function. The D function will cube its input, so we have to do 3a to the third, plus 7 times 3a to the second, minus 2. A little more opportunity for making errors here. When you are putting something like 3a in, you've got to make sure you cube the entire thing. So, cubing 3, we should have memorized 3 to the third is 27. So this would be 27a to the third, plus 7 times, and now I'm going to square 3a, which would be 9a squared, minus 2. Can't really do this with your calculator, except the number part. Negative 3 times 27 is negative 81, so we got negative 81a cubed, plus 63a squared, minus 2. And now we're done. That's the end of that one. Now the next one is even more complicated. Are we ready, or should I just wait a moment? Just wait a moment? Okay. This one's kind of hard for you to read what it's saying to do. It says do 6 times the C of 2n plus 1. So we're going to be multiplying 6 times something, and I'm going to use a bracket because I've got stuff to put in. I'm putting in 2n plus 1 for input into the C function. Okay? So I'm replacing x with 2n plus 1. Well, what does it do to it? It squares the input. So we're going to have to take 2n plus 1. My pen would start writing. All right, there we go. 2n plus 1 quantity squared. That's the first plug-in. Minus 2 times 2n plus 1. And then the function adds on 1 at the end, plus 1. And now we got to close the brackets up. Okay, I'm going to kind of wiggle this down here just so I can have some room. 6, then I bracket. I'm going to square this binomial. Remember how I taught you to do a quick squaring of a binomial. First term times itself, 2n times 2n would be 2n squared. 2n times 1 doubled would be plus 4n. And then 1 times 1 plus 1. Squaring a binomial the shortcut way. Then I need to multiply through by negative 2. So I have minus 4n minus 2. I had to distribute negative 2 over those two terms. And then at the end I have a plus 1. Yes, did I do something wrong? No? Oh, excuse me. Excuse me. Hello. I know better than that. How did I do that? I have no idea. I did it earlier today and I didn't do that. I have no idea. 2n times 2n. Hello, I said that, and I wrote a 2 instead of a 4. Ooh, thank you for stopping me before I went any further. I don't know how that happened. My brain was somewhere else, apparently. Sorry. Got it? 4n. Of course, it should be 4n squared. I don't know how I did that. But look at something in here now. Do you see anything that's going to be kind of convenient about this problem? Yeah. The 4n's wipe out because you've got opposites. 4n minus 4n. Yes. Oh, geez, I forgot to write the 1 there. That's when you stopped me and I didn't write the 1 because I was listening to you. Holy cow. And what about the numbers? We got a 1 and a 1 and a minus 2. So what's going to happen to there? All right. Yay. It's all goodbye. My goodness. Well, what do we end up with? 24n squared. That's the end of it. Okay, so the end is 24n squared after all that work and my stupid error. All right, well, that was on a recording. Didn't do that second hour. Oh, well. Here we go. Now, properties of the graphs of polynomial functions. Let p of x be a polynomial of degree n greater than 0. Okay, remember it has to be bigger than 0. All right. With real coefficients. Then the graph of p of x has the following properties. You will need to know these properties. It's continuous. All that means is that it's smooth, doesn't have any holes, no holes. All right. It has no sharp corners, so it won't be something like a V. It has at most n real zeros. Remember, n is the degree. Okay, so what that means is there can be up to n zeros for any polynomial function. Does it have to have that many? The answer is no, and I'm going to teach you how to know how many it could have. Okay, so if it were, for example, if it was third degree, how many zeros could it have? Up to 3, right? All right. So it also has at most n minus 1 turning points. Well, that would mean that 1 less than the degree. Turning points are relative maxes and mins. Okay, so if n minus 1, it just means if you had degree 3, then it could have up to 2 turning points. Up to 2 turning points. All right, and I'm going to show you pictures in a minute. It increases and decreases without bound. Now, as x approaches infinity, think about it, the x-axis. The left side is negative infinity. I can't get my pen to stay still. Okay, negative infinity. And the right side is positive infinity. And then you've got your y-axis, right? So what that's saying is it increases without bound on the left and the right. This side, x approaching positive infinity, that's on this side. And on this side, this would be this side, the left. Okay, that's what that is standing for. So we are now going to explain why each of these graphs is not the graph of a polynomial function by listing the properties that it fails to satisfy. This one has, yep, sharp corners. Okay. The second one has a hole or discontinuity. There is a discontinuity, which would mean it's not continuous. Oops. Come here. Got a little trouble with my... All right, there we go. And the last one here, it doesn't seem to ever go above 2. So it's bounded. All right, that one is bounded, which means it doesn't go to the fact that it says it's not bounded. Okay, this one's bounded. Now, The concept of end behavior, very important, and that's going to be the rest of what we're talking about today. The end behavior and turning points. The end behavior of a polynomial function's graph is the behavior of the graph as x approaches positive infinity, which would be on the right side of the graph, or negative infinity, which would be the left side. The expression x, see, I don't even know what to do. All I do is automatically say this. This says as x approaches infinity, that's how that's read. As x approaches positive infinity, what's happening? So end behavior will always be written as the following. The function, this will be the graph, okay? That's like your y. So the y values, what's it doing going up and down, all right? So this part's about what's happening this way or this way. So the graph is either approaching infinity or it's going towards negative infinity. So there's an option. It's going to be, and you could, all right, I shouldn't have written it like that. You probably don't like that. Let's just write plus or minus. How's that? I think you'll understand that better than me writing two infinities. So it could be going up or down. The graph could be pointing up or down. That's what that means. On the left side and on the right side, it could be pointing up or down. So the graph is going to approach positive or negative infinity on the right and or the left. This depends. So we're going to look at some graphs here, and we're going to discuss in general what's going to happen. So basically, we're describing what happens to the function as it travels to the left and then to the right. It is most helpful to either know what the function looks like and sketch it, or use a graphing calculator to take a look. If the end behavior is, this one means, this is just describing to you how to read these. As f of x approaches infinity, that would mean the graph is pointing up, and this means on the right side, okay? This would mean the graph is approaching negative infinity, meaning the graph is pointing down on the right side. This set right down here, this is saying the graph is pointing up on the left, and this is saying the graph is pointing down on the left. So you're going to have to know how to write all four of those and which one it's going to be, okay? I would be very focused right now because you need some, it can be very confusing if you're not paying attention and really thinking about what I'm saying to you, okay? Okay, you guys would know that this side's negative infinity, right? And you would know that this side is infinity, positive infinity. Vertically, this would be negative infinity. And vertically, this would be positive infinity, right? Going up and away. So we're going to describe the end behavior for each graph and determine if it's an odd or even degree, and we're going to state the number of real zeros. Okay, this particular one has a power of 3, so it is an odd degree. Then it says state the number of real zeros. There are 1, 2, 3. 3 real zeros. Hello, how are you? Good. So then we're going to say, all right, I've got 3 real zeros. That's because it crosses the x-axis 3 times, okay? Now, what is the end behavior? So what's the graph doing on the left-hand side? It's pointing up. So that's f of x, all right? The graph, what it's doing is the f of x. It means which way is it going vertically, all right? So the end behavior, f of x, is approaching, you just told me it's approaching what? Infinity. Okay, and what side are we on? The left. That's as x is going towards negative infinity. All right? So then we go and say, okay, what's the graph doing on the right side? It's pointing down. So f of x, the graph, is pointing down to negative infinity, and that is on the right-hand side. So that's as x is approaching infinity. The right side. Okay, this means the right side. This means the left side. This is what the graph is doing. Okay? All right, let's try another. So the next one we got f of x is 5x squared minus 3. This is an even degree then. Okay. The number of zeros is it has 2. There are 2 zeros. Right? And now we're going to discuss the end behavior. We're only looking at what's going on in the very left and the very right, not in between. Okay? So which way is the graph going on the left? It's pointing up. Okay, so f of x is approaching infinity on the left-hand side, which is as x approaches negative infinity. Okay, and then the graph is also pointing up on the right side. So the graph f of x is approaching infinity as x approaches infinity. That's up, up. So this was an up, up end behavior. Both of these are up. And this is just about the left side, and that's about the right side. It's always going to go that way. All right, so the next graph. This is uneven. Okay, how many zeros? There are no zeros. No real ones, at least. What's this graph doing? Oh, I forgot to do domain and range. We'll go back to that in just a second after I get you really straight on the end behavior thing, I think. That's the hard new thing. Okay, so this would be up, up again. So it's exactly the same as the last one. F of x is approaching infinity as x approaches negative infinity, and f of x is approaching infinity as x approaches positive infinity. Yes. Oh, good question. By the highest power. That's an even number. Good question. I don't know why maybe I didn't say that. Maybe I need it. I need to. You see that's even? Because it's a quadratic. All right, so we might notice something about the evens. Did you notice that these were both up and this was both up? This is an odd, and it's going to be switching left on one side and the other side. All right, it's going to be down, up, or up, down. Okay, that's what's going to happen with odds. Now, let's go quick, do domain on these and range. The domain for any odd function is negative infinity to infinity, and any odd function's range is also negative infinity to infinity. Domain for this even function is negative infinity to infinity. Both of these are the same, negative infinity to infinity. But the ranges are different on each of these. So we have to pay attention to where it bottoms out. What's the lowest point on this graph? Looks like 3, negative 3, excuse me. And it goes up, up, and away to infinity. And we're pretty good with domain and range at this point. Now, what about C? Looks like that's about 3, right? Man, I'm going with it because I don't know what decimal it would be. So let's just say the range is from 3 inclusive to infinity. Don't forget it's inclusive of those low points. All right, now we're going to do a big summarization. Okay, let's go real quick over here to the right side. What does this mean? X approaching negative infinity. What side's that? That's on the left. Okay. And as x approaches infinity, that would be on the right. Okay. So here we go. Degree 1. What is it? Its name. That would be a linear function. Okay. That's going to be linear. An example, f of x equals x plus 1. The general shape of a linear equation, and I want you to realize that I'm going to do everything based on positive first and negative second. Okay, so I'm going to draw 2 little graphies in here for every problem. Okay, so the general shape, if your slope is positive, how's the line go? Right, goes uphill. So that's the general shape for a positive slope. For a negative slope, it's downhill. Okay, so the sign of the leading coefficient, if it is positive, so I'm doing positive So all my first ones are going to be positive. So I'm just going to quick write positive all the way down here to help us fill this in as fast as we can. Okay, now I'm going to talk about both at the same time. So let's first discuss the positive. If it's pointing, a line is going uphill, what's happening on the left? Which way is the arrow going? Okay, it's going down. So on the left-hand side, f of x is approaching in negative infinity. Okay, and on the right, it's pointing up, so it's approaching positive infinity. And I don't write the plus sign when I'm doing positive infinity. It's just a waste. You don't need to. If you want to write a plus sign, it's okay. All right, so now I need to talk about the negative aspect of a line. If a line is going downhill, that would be when the leading coefficient is negative on the x term. Then on the left-hand side, the arrow is pointing up, so f of x is pointing towards infinity. And on the right-hand side, it is pointing down to negative infinity. Okay, the next one, the name is, degree 2 is a, quadratic. Example, f of x equals x squared. I'll just leave it at that. We already know and we've discussed what the general shape is for a parabola with a leading coefficient that's positive. It opens up on both sides. Okay, so f of x is approaching positive infinity for both sides. They're both pointing up. And if you have a parabola that has a leading coefficient that's negative, then it opens down. So what happens is both of the graph is approaching negative infinity on both the right and the left. So we fill in negative infinity for both of these. Okay, third degree, you ready? Is a cubic. F of x equals x cubed. So I'm going to do plus x. I don't know. It could have more stuff to it. It's just got to have a leading power, the highest power be 3. All right, so what's happening if the leading coefficient is positive? Right, then the cubic would look like this. Possibly. Well, I'm going to make a hump in it, so hold on a second. It might twist a little bit more than I just did it. It might go like this. Okay, which shows a possible 2 turns. Okay, if it's positive, the graph will point down on the left-hand side. So it's pointing to negative infinity. On the right-hand side, it's pointing up to infinity. If the leading coefficient is negative, then that thing's going to flip around and go like that instead. Which means now the graph f of x is pointing up on the left-hand side and down on the right-hand side. I hope we're getting this. That's why we're filling in so many. It's trying to pound it into your head. All right, now we've done the cubic. What else have we got? All right, we're ready to go with the quartic. The quartic, f of x equals x to the 4th, then maybe you'll say plus x squared in it. I don't know. It could have lots of x cubed in it, but as long as the highest power is degree 4, then it's a quartic. Any ideas? Let's see. It's going to do something like the second one, the one with the quadratic. It's going to do like a W, though. It might do a W if it's positive. So if the leading coefficient of a quartic is positive, f of x is going to have up end behavior. So f of x is going to approach infinity on both the right and the left. Or left and right, I should say. I'll keep doing left first. And then it'll flip over and make an M kind of thing, possibly, if it's a negative leading coefficient. So f of x is going to point down on both the left and the right. And finally, the quintic. And then we'll generalize. Quintic, f of x equals x to the fifth plus x cubed. I just made it up. I'm just anything, as long as it's got a highest power of 5. And so it's probably going to do something like which one? The cubic, yep. Okay, except it's even more dramatic. So if the leading coefficient is positive, then it's going to go, it could be a ripply thing like that. Meaning it has possibly got 1, 2, 3, 4, 5 zeros. And possibly 1, 2, 3, 4 turning points. All right, now that's if it's positive. So that means it's down on the left. F of x is approaching negative infinity on the left-hand side and pointing up on the right. And the last thing we're going to say on this chart is that if the leading coefficient is negative, that it's going to go possibly like that. And believe me, these can be dramatic points and valleys on these things. It's going to point up on the left-hand side and down on the right-hand side. Okay, so just get straight that f of x is which way it's pointing vertically, up or down, and these mean left-hand side and right-hand side. Oh, sorry, do you still need that? All right, let's generalize. So what did we see? We saw that if it was an odd degree, that it's going to have, and the leading coefficient was positive, then f of x is pointing down on the left and up on the right. We saw that if it had an odd degree and the leading coefficient was negative, that it pointed up on the left and it pointed down on the right. Remember, again, this is left and right. Left side of the graph, right side of the graph. Okay, and if it was an even function, if the leading coefficient is positive, then the graphs will point up on both sides. And if the leading coefficient, 6 minutes early, okay. Anyway, if it's negative, then it's going to be pointing down on both sides. All right, now let's look at a few graphs. Oh, turning points before that. The turning points are called extrema. These can be either relative maximums, maximum, I don't need plural, maximum points, or relative minimum points. We'll study these more later. For today, we're just going to identify the number of turning points. All right, so if we look at a graph, you can type this into your graphing calculator. But first, find the highest power. Yeah, so this is degree. What did it say to do? Determine whether the end behavior and the number of turning points. Careful. Graphing will be needed. Start with zoom 6 and then try zoom in, etc. All right. Looking at this thing. This one is degree 4, so I'm expecting it, since it's positive, to open up. I already know. But I don't know how many turning points unless I put this into the calculator. Okay? So I don't really, my calculator isn't working real well. I'll try and see how it comes out. I've been having some trouble with this memory on my computer. All right, so go into why it will not matter if you type this in descending order or not. Your calculator doesn't care. However, you have to know that it was actually x to the 4th Wait a minute. Oops. I'm on the wrong line. I'm going to get up there. Okay. X, and then you know how to put in those powers, and then don't forget you have to arrow to the right, because I do that all the time. I'm just putting it in descending order. What's the next one? Minus 3x cubed. Oh no, how'd I get a 33? It's going to take me longer than I got time just to type this stupid thing in, because I'm slow with this thing. All right. What's next? Minus 19x. And then plus 27x. And then plus 3. Okay, I just did mine in descending order. See what I can see. That's it. Okay, how do I know I've got everything I need? How do I know that I can see everything I need? Because I knew it should have what kind of end behavior? Up, up. Okay? I've got 1, 2, 3 turning points. Like this would be a relative min. Kind of looks like a rear end. You know what I'm saying? Like somebody's sitting there. Anyway. I don't know. I didn't have to say that, but I don't know why that came to my head, because I thought you guys were seeing something. So, all right. So let's do a basic sketch here of what it looked like, which kind of looks like a rear end to me. Whatever. All right. Now, what is it doing? As x approaches, okay, let's do the f of x first, though. I want to do the way the graph's pointing. I want to be consistent. So, yes.
You get like this, and then like
Did yours look less? Yeah. Did I have a wrong number typed in?
Well, I have one that it went up.
Does it do more of that?
I'm doing it like went up.
Does yours look more like that?
Yeah.
That's what I have in my notes. So I'm thinking maybe I had a number in there wrong. It's still going to do that, right? It's still going to have the same end behavior. All right. Now, but you still did this humpy thing, right?
Yeah.
Okay. So you still has the same end behavior I was describing. So f of x approaches infinity as x approaches negative infinity, and f of x approaches infinity as x approaches infinity. That's how you write it. How many turning points did it have? 3. Okay? That's all you had to figure out. All right, we'll look at more. Try, please, to start that book page. Have a nice evening. Sorry, I have to stop.